Start this last and afternoon session. And the first speaker of the afternoon is Enrique Álvarez, who will talk about existence and spectral stability analysis of a family of stationary periodic wave solutions for a modified Eckhouse equation with an additional term. Thank you.
Thank you very much for the presentation, and thank you for your assistance to my talk, considering that we are on the last day, the evening of the last day after lunch. Happy birthday, Professor Volker. For me, it's a great honor to have the opportunity of participating in this conference, which I think that one of its characteristics has been the super high level of the talks that have been given. I am not that familiarized with many of the topics of the talks. I did my PhD more in the area of partial differential equations. I'm going to talk about that in this presentation. But there's an intersection with the topics given during the week, because some of the tools that I use are related to spectral theory, and also some flocated composition also appears, like the ones that have appeared during this week in other talks. Okay, so I'll begin then. Okay, so this is Eckhouse equation, the first one that appears here. U is a complex number. It's unidimensional in X, and T is a positive. It's a positive value. Eckhouse equation is used to model ultra short pulse propagation in nonlinear fiber optics, and it also appears in the stability of weakly dispersive water waves. So that is Eckhouse equation. In this presentation, we will study Eckhouse equation with an additional term. That additional term is this one right here, a mu multiplying the partial derivative of u with respect to the space. Okay, so a brief justification of this term: the term appears as a linearization to avoid blow-ups in the solutions, and this takes us to the next point, the appearance of bounded periodic solutions. So the presence of this term is very important in our analysis in the existence part. I'm going to go to the outline in the next slide, and we are going to begin with the existence. And for the existence, this term is crucial. So that's the Eckhouse equation with the modified term. So I believe the next slide is the outline. So the presentation is divided in three big parts, I mean. The first part considers the existence of stationary periodic solutions. The existence is proven through Hopf bifurcation theory, okay, around the critical value. Hopf bifurcation theory is many times used to prove the existence of periodic traveling waves in the context of other equations. And Hopf bifurcation requires the presence of a parameter. And that parameter usually is the wave speed, the wave's velocity. In our case, however, the waves are stationary, so the velocity is 0. However, there is a parameter which is mu, the same that appears in the Eckhouse equation in its modified version. Okay, so after proving the existence through Hopf bifurcation, we obtain some approximate expressions for these solutions. This will be very important at the moment of linearizing, because we will need to linearize an operator around the solutions, and we don't have the exact expression of the solutions. We will use these approximations. Part 2 concerns the spectral stability problem. We set the problem through the perturbation equations, then with the Floquet characterization of the spectrum, and we decomposed the linearized operator. This decomposition will consist of three different parts. The first part being a term, a constant coefficient term, then a first order perturbation whose coefficients are known but are no longer constant. And then a second order um, perturbation with unknown coefficients. So we will have to do some estimates. And well, finally, the part three, we will analyze the spectrum of the free operator, and then we will answer the question if the eigenvalues which appear in the spectrum of the free operator are stable under the perturbations. Okay. So let's begin with the existence of the stationary periodic solutions. As I mentioned before, we are going to use the elements of Hopf bifurcation theory. Okay, so what do we mean by a standing wave solution? It's a solution of the form u of x, this exponential, and phi, where this phi is the wave's profile function. Okay, so we're going to look for solutions of this form. Okay, they are standing because there is no velocity which usually would appear in this part in the argument of phi. So our definition of a bounded spatially periodic standing wave, well, it is a solution of this form for which the profile is a periodic function of the argument and a fundamental period t. Okay, so this is the periodicity of phi, and this is the boundedness. The boundedness not only of the profile function, but also of its derivative. Okay, so this is only the definition. And substituting the type of solutions that we are looking for, substituting it in the modified Eckhouse equation, we obtain a second order differential equation for the profile function, which is number 3 right here. Okay. So since it is a second order ordinary differential equation, we can cast the problem as a first order planar system. So through these variables u and through this variable b, we obtain this planar system. Okay, it's a nonlinear planar system. And we make the observation that there is an equilibrium point at the origin independent of the value omega and the value mu. That is, for every value of omega and for every value of mu, real both of them, there is an equilibrium at the origin. Okay. So these periodic orbits that will bifurcate from the Hopf bifurcation theory, they will bifurcate around the origin. They will emerge. Okay, so we obtain the linearization of the system, evaluated at the origin, and now we have this constant coefficient matrix, which its eigenvalues depend on mu, both on the real part and for the imaginary part. And this is a very important concept for bifurcation theory. The structure of the topology of the solutions around the origin changes as we vary mu. So the origin can be a node, it can be a focus, or it can be a center, depending on the value of mu. Okay? And this observation is important. For positive omega, the eigenvalues become purely imaginary when mu is the value 0. Okay? So as the real parameter mu changes from a negative number, crosses 0, and then becomes positive, the topology of the solutions changes, which is a classical behavior when a bifurcation occurs. Okay, so, and this is observation that I was making, as we vary mu, the bifurcation parameter, it will determine which are the conditions under which periodic orbits for the planar system emerge. And this is a very important condition for Hopf bifurcation, the presence of purely imaginary eigenvalues. So the eigenvalues are actually crossing as mu varies from the left half complex plane to the right half complex plane, and there's a moment where they cross the vertical axis. Okay, so the usual existence results concerning Hopf bifurcation theory usually require, well, there are several trajectories which we could have taken. However, we take the current one, which begins by transforming the linear terms of the planar system to its canonical form, because this will enable us to obtain the required approximations, which will then be used for the linearization operator. That is what I'm trying to state, is that there are like weaker versions of Hobbes' existence theorem, which don't require everything that we are going to do. But we do them because it will be useful for us. So to transform the linear terms to their canonical form, we use this transformation T tilde, okay? And we use this change of coordinates. So the linear term of the planar system 4 will be transformed to its canonical form. So this is a canonical form of the linear terms. Alpha is minus mu over 2, and this is beta, the square root of mu squared minus 4 omega over 2. And f, well, f is 0. There are no linear terms in the first component of the system. And g tilde is all of this. G tilde is the considers the nonlinear aspects of the planar system. So now that we have the canonical form of the linear terms, we proceed to transform the equation to its normal form. So we do this by doing a complex variable transformation through u tilde 1/2 zeta plus its conjugate, and b tilde minus I over 2 zeta minus its conjugate. And we obtain the complex form of system 8, which takes this form, again, n corresponding to the nonlinear terms. We use this theorem. There exists a near identity analytic transformation, zeta equal to c plus s, such that system 9, which we already have it in that form, adopts this normal form, okay, where gamma and delta are analytic functions. We are going to mention in the next slide some things regarding S, because we need to get rid of the cubic and the quadratic terms that appear in the expressions. Okay. Except one of them, except one cubic term, which is the modulus of zeta squared times zeta. Okay. Plus terms, everything else can be regarded as terms of order at least 4. Okay. So the transformation S, which will take the system to its the normal form that we required, is constructed through 2 iterative steps. As I mentioned before, the first one gets rid of the quadratic terms that may appear in the expression. Okay, and then the second near identity transformation, which is given by 13, this is R, it gets rid of the cubic terms except for the modulus of zeta squared times zeta. And the composition of both 12 and 13 regarding Q and regarding R provides us the transformation S that we require to express the system. Okay, so now we go to the Hopf bifurcation. Under the aforementioned transformations, system 9 adopts the form 11, this being alpha, beta, gamma, and delta. And this is the existence theorem. Okay, so there exists a small epsilon, epsilon 0, such that system 11, which we have already transformed it to, has a family of closed periodic orbits. This is the form of the periodic orbits. The approximate radius, this will be very useful in the approximations to have an approximate radius. Okay, minus alpha prime zero, evaluated at 0 over gamma 0. Here is gamma. Gamma does not vanish at 0. It's a constant coefficient. And the derivative of alpha is minus 1/2. Plus terms of order mu squared. Then we have the gamma over here, and their period is given by 2 pi over the modulus of omega. Okay, so this is 11. So now through the near identity analytic transformations, we have transformed our system to this form 11. And the existing result is stated in terms of this of this number 11. Matthew. Do you mean to this slide? Yes. Z is a function of t. Yes. So these are the closed orbits in the plane. R of mu is a constant. It depends on mu. Yes. It's a family of closed periodic orbits around the origin. Okay. But yes. Okay. Where was I? Okay, so this is the existing result. Okay, so for positive omega and the q and the critical value mu is equal to 0, there exists this epsilon 0 sufficiently small, such that for every mu, positive mu between 0 and epsilon, there exists a unique closed periodic orbit solution for the planar system 4, whose amplitude and fundamental period behave like they grow like the order of the square root of mu. Okay, and their period behaves like this, 2 pi over the square root of omega. Okay, and for values as the values of mu get bigger and bigger, these orbits begin to break. So this only works for very small values of mu actually. Anyway, so I want to make a remark here. The existence of these solutions is for the planar system, like for in the context of like seen as a dynamical system, a planar system. There's a distinction between the solutions of, of these orbits in the plane to the solutions to the entire Eckhouse equation. Those solutions are mentioned in the next slide. Okay, so this is the existence of the small amplitude stationary periodic waves as solutions to the Eckhouse equation. Okay, so making a difference between the planar system and the Eckhouse equation. Okay, so again, for positive omega and for this epsilon 0 and for mu sufficiently small, we will have solutions of the ones that we're looking for, the stationary periodic solutions, their fundamental period being this. The first equation concerns their periodicity, and the second one concerns that they are bounded. And they are bounded and they grow as mu grows. They grow as the square root of mu. Okay. So now we have proven the existence of the solutions for the modified Eckhouse equation. Now we are going to linearize the operator around them, but we need more expressions, more information about the solutions themselves. So that's why we went through this way of the analytical transformations. So to obtain approximate equations of the periodic orbits, we transform back to the original coordinates through T tilde, which was our change of variables transformation, and then the inversion expression, and by incorporating the polar coordinates. Okay, so we finally have some expressions um, of the waves themselves. Okay, so they are parameterized by mu, and they are of the form u0 mu plus terms of order mu, b0 mu plus terms of order mu. u0 mu, we know them precisely. It's the square root of mu times cosine the square root of omega times x. And b mu, it's mu to the 3/2 over 2 cosine plus this square root of mu squared, and minus for omega 2. Okay, so I want to make an observation here. In many cases, when the spectral stability of the solutions, for example, of periodic traveling wave solutions, is studied, only the first approximations are the ones that are used, constant coefficients approximations. So in this case, we are taking a further approach, and there's a reason why we did that. This will give us a first approximation with constant coefficients, and then a second perturbation, and then a third one with coefficients, unknown coefficients. Okay, so part two, the spectral stability problem. We begin by considering a nearby perturbation B of a bounded periodic stationary solution. Okay. This perturbation can be decomposed into its real and imaginary parts, and after the substitution into the modified Eckhouse equation, the leading approximation is given by the linearization around phi, which is this one right here. Okay. Now we search for perturbations of this particular form. The exponential function evaluated at lambda t times w, where lambda is a complex number, and the components of w are in L2, obtaining this eigenvalue problem. In one of the talks during this week, someone mentioned about the potential being periodic, and in the context of L2 having a continuous spectrum. Was that right? I believe so. So this is going to be important in the following slides. Okay, so we define the linearized operator around the wave acting on L2 times L2 with dense domain dissolvable space to guarantee the existence of the weak derivatives up to order 2, which we need here and here. Okay, and the bounded and periodic coefficients. Okay, so we haven't done the linearization yet around the particular approximations. In here, up to this point, phi and its derivative only appear in general. We have still to do the substitution of the approximations that we obtained in the last slides. Okay? So, the definition. A bounded periodic wave is spectrally stable as a solution to equation 1. Equation 1 was the modified Eckhouse equation. If it's L2 spectrum of the linearized operator around the periodic wave solutions satisfy that it doesn't have any element. The spectrum does not have any element with positive real part. Okay. In other case, we say that they are spectrally unstable. Okay. So, as a kind of a spoiler, these waves are going to be spectrally unstable. So, that is why do I mention it at this point? Because it suffices to prove, it is enough to prove the presence of at least one element with positive real part. Proving spectral stability is much harder because you would need to prove that all of the elements of the spectrum are contained in the right half complex plane. But it is not our case, not in this problem. Okay, so I mentioned before, Floquet spectrum appears in the presentation. The spectrum can be parameterized in terms of the Floquet multipliers as the set sigma theta of complex numbers lambda, for which there exists a bounded non-trivial solution of the boundary value problem. Okay, so the first two equations correspond to the eigenvalue problem still, and these are the boundary conditions with e to the y theta. We are about to get rid of this part also, or in the following slides. Okay, so the Floquet spectrum sigma f is defined as the union of this partial Floquet spectrum, as theta varies between minus pi and pi. And I mentioned about the spectrum being continuous for the following reason. For each theta, each of these sigma theta are just going to be discrete points. Well, if you hear me, I can. Okay. The sigma theta are going to be discrete set of points. And as theta varies between minus pi and pi, there's going to be these sigma theta are going to form a continuous curve. Okay. Entonces, sorry, sigma theta are going to be discrete sets of points for each theta. And as theta, we vary theta between minus pi and pi, this complete, I mean, not the partial anymore, but the entire spectrum is going to be a continuous curve. That's what I mentioned the other thing about the spectrum being continuous, also in this case. Okay. Now, we will have to remove the theta dependence in the boundary conditions. So to do this, we can pose the problem in an appropriate periodic setting. Through the following block weight decomposition, we make this change of variables to pi x over t mu, and we change these u's. Okay, so now this enables us to recast the spectral problem as lambda u of u1 and lambda u2, and now the parameter theta is incorporated like if it was in the derivatives in here and in here. Okay, and these are subject to 2 pi periodic boundary conditions. So the problem has changed, and since that since we only need to find one eigenvalue with positive real part, this will enable us to work only for the case theta equals to 0, which will simplify a lot of our operators and the work that we're going to do as follows. Okay. But first of all, we have to do the linearization around the waves. We have not used yet the approximations that we found through Hopf's bifurcation theory. Okay, so I'm going to return, I believe, 2 slides. Yes. We're only working with the partial spectrum concerning sigma 0. Yes, because it is enough to have one eigenvalue with positive real part to prove the spectral instability. Yes. So since sigma 0 has a positive, an eigenvalue with positive real part, we have the spectral instability. And the reason why we choose theta equals to 0 is because it simplifies the calculations here. Okay. Up to this point, we have not used the approximations that we have for the solutions, but we are going to use them now. Okay, so substitutions of the expression for the approximate solutions, we have these coefficients. Okay, we substitute here the phi and the phi prime some in the corresponding places. Now, we make these b zeros, beta zeros, b1, b1. The a's and the alphas are the ones here. Okay. However, the reason why we get perturbations with unknown coefficients is that, well, the ones that I'm going to return to the slides. These are only approximations. We don't know what happens with the higher order terms. Okay, so that will produce perturbations with unknown coefficients. Okay, well, now we are getting closer to the decomposition of the linearized operator. So for h theta, we have h0 theta plus v1 plus v2. All of them defined for theta. Sorry, there should be a minus here, which I omitted. That was an error. Okay, so h0, constant coefficients. b1, the coefficients are not constant. However, we explicitly know them due to the approximation of the waves. b2 contains the perturbation with the unknown coefficients. Okay. The eigenvalue problem can be regarded as a perturbed spectral problem, h0 plus v1 plus v2. Okay. we are going to be able to determine the spectrum of this operator, and then see if the what's the behavior of the eigenvalues after these perturbations. Okay, so now we are getting to the spectral instability analysis of part 3. As I mentioned before, it will suffice to it will be enough to analyze the case theta equals to 0, in which case the operator H0 is this one right here. Okay. So this component is a negative multiplication of this one right here. Okay. The spectrum of this operator, it's completely contained in the imaginary axis. The spectrum is this one right here. So it's completely contained in the imaginary axis. In other problems, for example, the one that I studied in my PhD thesis, the this first operator had already eigenvalues with positive real part, so that made it easier. This is very sensitive. That made it easier because we just had to prove that this eigenvalue was stable under perturbations, and that an eigenvalue with positive real part was going to survive the perturbation. Okay. However, um, this case is more complicated because the operator obtained as a first linearization does not have this case of obtaining an eigenvalue with positive real part. They're all imaginary. So we need to have make some extra work. Okay. We focus on the eigenvalue I12p squared. This eigenvalue has multiplicity 2, and it is obtained through B12 and B22. That is, substituting k is equal to 2 here, we obtain this eigenvalue. Okay? This eigenvalue undergoes a splitting under the action of the first perturbation, and we are going to see that the splitting goes, I mean, at least one of them, one of these two eigenvalues that split into the unstable right half plane. Okay? And then that an eigenvalue with this same property will still remain under the action of B2, which is the second order perturbation. Okay. So at this point, I would like to mention the influence of Professor Miguel Ballesteros, um, who well, who taught me these tools more related to spectral theory, which I didn't study during my PhD studies. So I didn't have the required tools to solve the stability problem. So he was the one who had these ideas that are going to follow. Okay, so we decomposed the operator H as H0 plus B, where B is the sum of both of the perturbations, and P0 is the orthogonal projection on the subspace associated to the eigenvalue. We consider gamma to be a closed curve around this eigenvalue that only encloses E0 as a spectral point of H0. Okay, so we make P equal to this projection here, 1 over H minus zeta, and we begin to decompose it in several parts. So the first decomposition concerns this P sub P plus P sub R, okay? And well, these are the first terms of this sum, 1 over H0 plus this B1, and then this B of R, okay? Which consists entirely of terms of order mu squared, as is going to appear in the next slide. Okay. Yes. Oh, A0 is the eigenvalue. Yes. Okay. Now this proposition, which we only include the sketch of the proof, um, there exists a constant c such that for each c in gamma, we have this approximation of p0 bp0 times by approximated it by p h minus e0 and p. Okay, so since the order of the term pr in this one right here is of order mu squared, we may proceed to estimate only the terms concerning piece of p and piece of p over here. Okay, so well, we do some substitutions here, and we obtain that this expression in the left and p0 b p0 are close enough in terms of order b squared. Obviously, recalling that h0 p0 is equal to e0 times p0. So this will be useful in the next slides. Okay, the eigenvalues of p0, v1, p0, we diagonalize this matrix, and we find effectively a positive eigenvalue, an eigenvalue with positive real part, okay, which is this huge expression right here, okay, and we proceed to show that this implies that p h minus e0 p has an eigenvalue close to e0, okay, which and that would with that we would have the spectral instability then. Okay, so let gamma lambda 0 be a sufficiently small curve that are around lambda 0. Lambda 0 is this eigenvalue. Okay. And for C in gamma in this curve, it holds that this integral will have the same value as the 1 over h minus c. So we take first p tilde, p plus p tilde is the identity. We have the h minus c can be decomposed as php minus pc plus p tilde h p tilde minus p tilde c, and that the inverse of h minus c, it's just this expression. Okay, so the integral on the left is going to be the sum of these both integrals with only this one remaining. And the corollary, which we need, is if this integral is distinct from zero, then the one concerning h minus c will also be distinct from zero. Yes, please, the projection. Yes. For the calculation of the spectral instability? No, only the presence of the positive real part. Like, do you mean if they would like return to the? But I believe that the with these approximations that wouldn't happen. Okay, let me see in this next one. Okay, wait. This is the theorem, also only a sketch of this proof. The spectrum of the linearized operator H acting on H2 pair times H2 pair has an eigenvalue with positive real part. It follows from the fact that this is a non-zero projection, and the entire projection on the left can be approximated by the terms of this one, non-zero, plus terms of mu squared. for me small enough. And this will take us finally to the spectral instability of the family of periodic stationary waves, which was the original problem that we, yes, Miguel. So this will take us to and well, we end with the spectral instability of the periodic stationary solutions. That is the spectrum of the linearized operator around the waves contains elements with positive real part. And thank you and congratulations again, Professor.
Thank you very much. There have already been several questions, but are there more questions at this point? Are we still on?
Yeah, I mean, there's some difficulties because this is non-self-adjoint, everything is non-self-adjoint. So there was a problem with this spectral analysis because the operator is not self-adjoint. So we need something like a spectral theorem, for, in this case, for the non-self-adjoint operator, in which you get a vibration of the operator in terms of non-self-adjoint operators that are in finite dimensional space. So this is what kind of what made it a little bit complicated, no? What we did. Yeah, there's a comment.
That's why I mentioned at certain point of the presentation that many of the tools, especially the last part of the presentation, um, I didn't know them from my PhD. It was Miguel who gave me the way to follow.
Thank you for the beautiful talk. Now what you present in the end is a kind of no-go theorem, or I mean, you were hoping for stability, I suppose, to prove it in the beginning, and then you prove instability, or was it all the way meant to be stability, or is there a modification that you would know how to put up to have then stability of periodic solutions? Modification of the equation.
I believe I was looking for special instability, spectral instability since the beginning, to to the to the um, to the easiest way to prove it with concern to spectral stability. Now, about making a modification on the equation itself to make it to make the to if there's a possibility of making the solutions spectrally stable, I have not thought about that problem, but I think it's a good way to follow. I would say probably like using some weighted spacers or something like that that would pull the spectrum to the. Okay. So in the exponential growing of the perturbations, considering the periodic solution, yes. So there's a growing distance between them as time passes. It's exponential distance. Yes. So here I'm going to return to the form of the perturbations. Do you remember that well, we remember in general that the perturbations had this form, a to the lambda. So the presence of an eigenvalue with positive real part will get farther and farther away of the periodic solutions. Thank you.
More questions or comments? If not, let's thank Enrique again.